All right, guys, so today we are going to be working on our first set of notes over measurement. And this is going to be really important because in science, especially in physical science, when we're dealing with so many numbers and the math behind it, we need to make sure we're taking accurate measurements and we're being precise with everything, which happens to be the first two vocab words we are going to talk through. So I'm going to be walking you through how I'm taking my notes along with you, and every few slides I'll stop and show you what my note page looks like. You're going to be starting with concept 2, and it has the little bullseyes on it. Mine is a little rolled up, so excuse that. But let's go ahead and get started talking. So when we talk about accuracy, this is a really complicated looking definition, and I have a simpler one as well, but you're going to want to make sure you put this one down so that if this is referenced in any of the quizzes or tests you're taking, you already have the information. So accuracy is the degree or level that the experiment result is going to agree with an accepted value. So it sounds like a bunch of words, but it's just saying how correct a measurement is. So if we already know that, let's say a car is driving 65 miles an hour and we're testing a radar gun out, and the radar gun is reading 72, then that's not going to be very accurate because we know what the car should be traveling. Now, precision is the degree or level that measurements agree with one another. So we don't care if they're necessarily right or wrong, but that all of the different measurements we're taking seem to be close together. So this can either be how specific a measurement is or how consistent or constant a whole bunch of measurements are to each other. We're going to look at these 4 bullseyes. And in class, if you were there, remember we had someone shooting paper balls into the trash can, and we were looking at all of the different trials, essentially, that they did. So the very first, actually, I don't know if you can see this. There we go. The very top left bullseye. So that's showing 4 dots clustered pretty closely together and in the middle. So we're assuming that this is like a dart bullseye. And so the closer to the middle, the more on goal or on target you are, meaning that this is a representation of accurate information. So we're hitting the goal the way that we hoped or knew we wanted to. But also, all 4 of the different dots are located really closely together, which means that they're also precise. So this one is precise and accurate. Now, if we look at the one next to it on the top, we're not inside the bullseye of the target. So we're not really accurate. We didn't hit the goal, but all of our spots are still clustered closely together. So they are precise. And then down in the bottom left, while we hit the bullseye with all 4 of our shots, it's accurate because we got it in the target, but our dots aren't actually lined up that close together at all. So this is an accurate result that's not precise. And then in our last one, this is what it looks like when I play darts. We have 4 different shots that are all spread out along the board. None of them have hit the bullseye, so we're not accurate, but also none of them are even close enough together to consider, so they're also not precise. So let's run through a couple of our examples here. So example number 1, if a student knows 85% of the material for a test, but gets a 70% on the test, is that measurement accurate, precise, or neither? So for accuracy, we're trying to hit a goal. So did we hit the goal where we know 85%, but we didn't get an 85%? So therefore, it's not accurate. And if we look at if it's precise, precision is depending on how many of our results or tries are close together. But we only have 1 try here. So this is not accurate or precise. There we go. But I also want you to note in your notes that the reason it's not precise is we only have one measurement. We need more than one measurement to get precision. In example 2, Mrs. Joyner's dog Millie, she's known to weigh 65 pounds. Millie goes to the vet and she's weighed 3 different times at 71 pounds, 70 and a half, and then 70.1 pounds. Are they accurate, precise, or neither? So if our goal is, or our target is at 65 pounds, that's what we know to be true, the measurements that we got are not close to 65. So this is not accurate, but all of our measurements are pretty dang close together, so they are precise. Okay, so going in and looking at how I've taken these notes, I don't have a whole lot of different color pens just for the sake of time and trying to get this video done. But I did make sure to highlight specific words, and then if there were any questions that you had from anything, make sure you put it in a different color pen or you note it some way so that we can answer those in class. So with our accuracy definition, I highlighted the word because it's a vocab, and then I highlighted the simpler definition because that's what helps me to understand what's going on. This other one up here, it's nice. It might be useful when it comes to a test or a quiz, but this is what helps me understand what accuracy is. And the same thing with precision. This whole first part was kind of like, okay, what does that mean? But really, I'm looking at how consistent multiple measurements are to each other. So I just highlighted that second part down here. Then you'll notice for my bullseyes, I did label them because this is a really great visual to have information on later. And I just used an abbreviation for precise or accurate and crossed out what it wasn't. Then I also wrote down the answers here that we discussed, but I also made a note that it's not precise because we only had one result. Okay, so now we're talking on when we collect data, usually we're going to be collecting multiple, at least 3 different trials because science likes the number 3. So when we're doing that, we want to find the average of our different results so that we can get one number to work with in calculations. So when we're doing the average, we add up all the values that were given as our results, and then we're going to divide by the number of numbers that we have. So as an example, Callie measures her flower to be 30 centimeters tall, Jeff measures it to be 45, and Liam measures the plant to be 36 centimeters tall. Find the plant's average height. So to do that, we're going to take all of the results that they got, and then we have 3 different result numbers, so we're going to divide by 3. And that is going to simplify down to 37 centimeters. Now remember, in science, you need to put a unit. No naked numbers, dress it up in something pretty. In this case, we're talking about centimeters. If you had just told me the answer was 37, I wouldn't know if you were talking about bumblebees or pieces of spaghetti or what was going on. I would just try to make up my own unit of measure. It could be 37 miles. That's a pretty tall flower. So make sure you put your units. So in science, we use what's called standard units. So a standard unit, the standard is an exact quantity that we use for comparison. So somewhere in, I believe it's Switzerland, there is actually like a vault, and they have a standard unit of measure to tell us what an inch is supposed to be, or how much a kilogram is. And they have different items that represent the standard or the way we compare all other measurements to make sure that they all line up the same. And then the SI system, it actually stands for the international system, but in like French, I think. And this is the system used by scientists around the world to make measurements. So in the United States, we use the imperial system. We like feet in inches for some reason, but the SI system is a standard unit that scientists are all going to use. So we're going to talk about what each measurement is in the standard system that we will use in science. So every type of measurement has a base unit, and we use prefixes with those base units. So the part that comes before the unit that are based on multiples of 10. So that's what we're going to go through now. So the length is a unit that's a distance between 2 points, which I'm sure you guys are pretty aware of. And we use the meter, or a lowercase m. Make sure you write both of these down. And yes, it does need to be lowercase. A capital M means something different in science. And we usually use a meter stick or a ruler for this, but you want to make sure that it's measuring in meters and not just inches and feet. Then for mass, the mass is how much matter is in an object. And we use kilograms, and that's represented with kg. Again, both lowercase. Make sure they're both lowercase. And we use a spring scale or digital scale to read these. Okay, let's just take a look at this real quick. So I have standard highlighted because it looks like it's a vocab word, an exact quantity. And then SI system, used by scientists to take measurements. Then for the units, for length, I just highlighted distance. And then I made sure to highlight the unit, the name, and also the letter. I didn't highlight how we measure it because I know that if I can come find length, then I can find how we measure it. Then mass is amount of matter, and we use kilograms, so I highlighted those things. I also boxed those in because these are going to be important things that we are going to use throughout the entire year. So volume is the amount of space that occupies an object. So mass is how much stuff is in that space, but volume tells us essentially how much space we're using. And the unit for that is a liter, so kind of like a 2-liter bottle of soda. It doesn't matter how much the soda weighs that's in it, but it fills the same space bottle as any other liter or 2-liter bottles. And that's a capital L. Again, make sure you're using a capital L. And we measure this using a graduated cylinder, which is that picture over on the side of the slide, or we can calculate it, which we will do later on. And time is a interval between two events, which is probably a word you've never really thought to define, but there it is. And we use seconds, which is a lowercase s. Sometimes you can write SEC, but as we get a little bit farther along and the math gets a little bit trickier, S is just as easy to use. And then we usually use a stopwatch to measure that. Right, then for temperature, we're measuring the amount of heat in an object. And we'll talk about this a lot later, but we're talking about the amount of heat, not how cold something is, but how hot it is. And in temperature, we use kelvins, which is a K. It's actually fairly close to Celsius, but definitely not Fahrenheit. So the metric system is what uses Celsius, imperial uses Fahrenheit. And we measure that using a thermometer. Now, temperature conversions. Sometimes you're going to get something in Celsius or Fahrenheit, but we need to actually flip it over to Kelvin. So there are two equations that we need to use for that. Kelvin equals degrees Celsius plus 273, and degrees Celsius to Fahrenheit, we're doing 5/9 times the degrees Fahrenheit minus 32. Then to go the opposite way and go Fahrenheit or Celsius to Fahrenheit, we're doing Fahrenheit equals Celsius times 9/5 plus 32. So remember, you can use your notes on your quizzes and your tests. Make sure you write this down clearly so that you can see exactly what's going on. All right, so let's go through this example here on how we're going to convert our temperatures. So Mrs. Smith is going on vacation to Greece for her anniversary, and the weather is predicted to be 27 degrees Celsius. Mrs. Smith lives in the US, though, and doesn't know what to pack for this weather. Help her determine the temperature in Fahrenheit so she can pack. So I'm actually going to move over to my camera real fast and show you how I would set this up. Okay, get in nice and close here. So we have 27 degrees Celsius is what the weather is going to be. but Sheila's in the US, so they say they want us to help determine the temperature in Fahrenheit. So I like to highlight the key words that are in word problems so that when I go to set it up, I know exactly what I'm doing. So I have degrees Celsius is 27, and then degrees Fahrenheit is what we're looking for. So I'm going to look at what equation I can use. This one right here is obviously going to be my easiest choice because it gives me the answer for Fahrenheit. So I'm going to rewrite the equation without any of my numbers put in it yet, just the variables. So Fahrenheit equals Celsius times 9/5 plus 32. And then I'm going to plug in what I know. So Fahrenheit equals 27 times 9/5 plus 32. Now, when you go put this in your calculator, you actually have to do some work for the calculator and make sure it knows exactly what you're saying. So what I'm going to do is I'm going to take this first phrase, 27 times 9/5, and I'm going to make sure to use my parentheses around my fraction so that it does that as its own separate idea. So I'm just putting in what's inside these parentheses and pressing enter. Now I'll take that number and add 32. So my answer is in Fahrenheit, we get 80.6 degrees. All right, so in your notes, you're going to notice it says practice time. I want you to go ahead and practice converting 23 degrees Celsius to Fahrenheit, then 48 degrees Fahrenheit to Celsius, and 83 degrees Fahrenheit to Kelvin. And we'll come back and we'll talk about these in class, so make sure you bring your notes the next time you're in class, and we will make sure they're all set. We're going to talk prefixes real fast. So prefixes are the part that comes before our unit. So if we talk like a centimeter, centi is the prefix to meter, which is our standard unit of measure for length. So we're going to go ahead and fill these in on our notes, where mega is a capital M, kilo is a lowercase k, hecto, which we don't hear that too much. You might hear like hectare, and that's like a measure of acreage. Deca is DA, and then we get down into our smaller ones where it's actually smaller than one whole unit. So deci, centi, milli, micro is actually, I'm going to show you on my notes. It's kind of like a weird M-U combination. And then nano is an N. So let me show you what that micro looks like. So micro is like this swoopy M/U looking thing. It's like a U with a front tail too. So these are all the prefixes you might see in front of the words that we have. And your base units are going to be your meter, your gram, your liter, and your second. So everything where it says unit right there in the middle, that's where your base is. Everything above that is bigger, and everything below that is smaller than 1 unit. All right, so now we're going to talk about how you convert numbers and units, because there are going to be quite a few times where you have to take an item and you're going to convert it into something else. So we might be taking, let's say we have like feet and we're trying to convert it to meters. So the steps that are in your notes is you write down the given number in the unit, then we're going to draw a times and then another fraction. And we're going to fill in the conversion factors, which I'll show you in a second, making sure units match on the opposite sides to cancel out. So we're talking on opposite sides of the fraction bar. Then you multiply it like a fraction, so top goes with top and bottom goes with bottom. And then you actually do the division of the fraction, so top divided by bottom. Let me go ahead and show you what this means with our first example here. Okay, so how many meters are there in 48 kilometers? So, okay, I messed up the first time. So we're gonna start over. So how many meters are there in 48 kilometers? So I'm gonna have 48 kilometers, and then it's a whole number, so I can put over 1, and then I'm gonna multiply it by another fraction. So my goal is I want to put kilometers down here so that they cancel out, because anything over itself is just 1, so they're going to cancel. And I'm going to try to put meters up here. So I'm trying to figure out how I can make kilometers and meters match up. Well, if I look back here at my chart, I can say, okay, 1 kilo of anything, so 1 kilometer, equals 1,000 of those base units. So 1 kilometer or kilometer is going to be the same as 1,000 meters. And then I just cancel out those units because one's on top and one's on bottom. And I take my fraction and I multiply straight across. So numerator with numerator and denominator with denominator. So I get 48,000. And then my units are left over as meters over 1, which essentially doesn't exist. So my answer is 48,000 meters. So how many kilograms are there in 45,456 milligrams? So I'm going to write down what I'm starting out with. 45,456 milligrams on top of a 1, because that 1 is always there under whole numbers. It's just imaginary. And then multiplying it by another fraction, I'm going to put milligrams on the bottom so that these can cancel out. And the one that I want is going to go on top. But let's actually look at our conversion first. So milligrams is down here. So what I'm going to do is say, okay, if there's 1,000 milligrams in 1 gram, so 1 base unit, how about I put it into grams first, because I already know what that is. So there's 1,000 milligrams inside 1 gram. And I can cross these guys out because I already know they're going to cancel, just the units. But my goal is still to end up with kilograms. So now my top unit is grams. So I'm going to put grams down here on the bottom so that they cancel out, and my goal unit, which is kilograms, up here. So now I'm trying to figure out how I can relate grams and kilograms. So I look back. Kilo is 1,000 of whatever unit we have. So 1 kilo is 1,000 units. So 1 kilo is the same as 1 kilogram is the same as 1,000 grams. So now I can cross these out, and I'm going to multiply my numbers straight across. So 4, 5, 4, 5, 6 kilograms. Right now, space there a little bit. Divided by, here I have 1 times 1,000 times 1,000. That's a lot. So this actually gives me a denominator. I'll try to get my paper scooted over. Of 1 million. But there's no units down here. So now I'm just going to actually do the math. And you can type in your calculator, or you can just move the decimal over. It's been a long day, so I'm going to type it into the calculator. No shame in that. And I get 0.045456 kilograms. Now we'll talk about scientific notation a little bit later, and that's going to make these types of problems a lot easier because we'll learn just how we're going to shift just the decimal over. Move through the slides. So your second set of practice times that I want you to do before you come to class next is converting 6.1 kiloseconds to seconds, converting 0.859 milligrams to centigrams, and convert 65.4 meters into millimeters. So bring those to class when you are all done, and we will talk about them later.